Alright, this week let's look at beam elements inside LSDYNA and how you generate contact with solid elements. Not a common problem, but this is actually in response to one of the questions from the Answers Innovation Forum. Basically, I sometimes answer question here. In this case, I thought this sounds like a topic I can cover, but I'm not gonna solve this problem, but instead I'm gonna do something relatively similar to this. Basically, look like this. And I will talk a little bit about how contact is generated, how you can overcome things like this with a different type of contact formulation where you can basically allow the edge contact to basically occur, like right there. In some cases, we don't have that edge penetration, and that's really the kind of problem that we usually run into. And there's also the problem of having correct beam-to-beam contact and shell edge contact, which sometimes presents some certain challenges that we want to be able to overcome. Okay, and we're gonna do a problem like this today. Before I do that, agenda for today is that I'll talk a little bit about beam sections and beam integrations real quick, just to present basic option. These things inside Workbench, it does a decent job of choosing the right default for us. And then from there, I'll also talk a little bit about different kind of contact that is available inside LSDYNA that we can use to generate the correct type of contact behavior inside the Dyna model. We do a very simple problem, but the idea is that with a very simple problem, we can translate the response to something that's more generic. Okay. All right. So basically, in Dyna, you have a lot of different kind of beam formulations. The default one from Workbench or from Dyna is the Hughes-Liu cross-section integration. It's pretty commonly used. Sometimes I also use a discrete element for beam and cable. I use Alform 6 a lot for a lot of the problem I do. I don't actually do a lot of problem that's directly just by converting things to beam. But the 1 and 6 are the most commonly used one for me. I'm sure there are other reasons for using other things. I've also used spot welds before for beam Alform 9 for modeling spot welds, which are basically connecting two nodes with a beam element, which are modeled like a spot weld. These are the different type of beam element formulation you can induce inside LSDYNA. Now, with any beam element, you have to sort of define the cross section, right? The integration methods. So there's a lot of different kind of cross section in which you can directly input into the integration beam method. With the integration beam method, these two cards usually come together. So inside LSDYNA, if I look at my beam element. My integration beam element, right? Usually you have your integration beam and you have your section beam. These are usually two things that will come together when you use beam element. You always almost write these two things together to define both the section behavior for the beam as well as integration methods and the cross-section area and the dimension of it, right? Similar to what happens inside Workbench. Inside Workbench, obviously, you can convert the solid body from here. Like this is what I generated my original body look like, but I can convert that inside Space Claim to turn that into a beam element. Within the beam element, and then have a cross-section card, cross-section model, which is going to define the cross-section of the beam, and that gets translated into an integration beam card, which is going to be what's going to be used inside the LSDYNA model. Okay, and that's the basics. There's a lot more I can talk about, but I think that's sufficient for today. In terms of the contact, there are different contact, right? So the Workbench, if you use Workbench, automatic contact is automatically generated. This automatic node surface contact can be generated inside Workbench relatively easily. And what this will allow to do is allow you to be able to model the beam edge as essentially a set of nodes, right? It's a node set that you're essentially defining on the slave side. On the master side, you have the segment, which is a segment of your solid element, and that's where the contact interpenetration are prevented. Usually, if you define a depth of 5, it allows you to have a better edge detection, and that's usually what you want it to do to generate a beam to surface contact, is to make sure you have a depth of 5, which allow you to define the edge of the segment to better detect the beam element. Software Code 2 is better for segment-based contact, and that's when you have this corner edge contact that exists in the solid element side. Software 1 is better if you have like a very soft material on one side and a very hard material on the other side, and that's the kind of thing that's relatively standard that we can work with. Okay, so something that look like this with a depth of 5 and soft of 2 allows you to basically do a still automatic node to surface contact. The nodes are the beams, the surface are the segment for the solid elements. What we can also do is to have a much better detection. Say for example, If we only do surface automatic surface contact, what happens is that you have this initial penetration right there that happens between the automatic and nodes of surface contact. That doesn't actually do a very good job, right? You can see it doesn't really detect that end of it until you get to the segment. Until you have some penetration that eventually gets resolved, is because that's the contact starts later in that contact pair. It's actually not correct. What we want to do is have the edge of the solid element actually detect with the beam element, and the way you do that is by basically use uh, a mortar contact, which allow you to detect the edge correctly, right? This edge has the beam integration, which has the cross-section area accounted for, and this give you a much better contact definition and contact behavior than you actually look for in the model, right? In this case, you use the mortar contact. The problem with the mortar contact is that it's usually used for implicit. It's also extremely expensive, right? So even though the mortar contact is like almost like a magic bullet, it's almost 10x more expensive than a regular contact. So you really don't want to use it for a very large model. It's probably not going to do a very good job. It's just going to slow the model down by a lot. What we can also do is to use automatic general contact. It's not used for beam to the solid element edge contact, but it's very good for shell edge to edge contact or beam to beam contact. So if you want beam to contact beam, you want to use a underscore general option for the automatic contact, which is going to give you a much better behavior for this kind of problem. Okay, so I already showed you the results right here, right? But let's look at the basic model setup so you understand what was done. In this case, what I have is basically 3 different beams, right? We have some common cross sections and some shape that I'm defining. For this beam and this beam, I'm contacting this surface, right? And then for this beam, I'm basically contacting at the edge, which is what I want to be able to resolve. Is I want to be able to generate a beam to solid contact such that the beam can be correctly established relative to the contact with the solid element, but I also want to be able to define the edge contact correctly. As you can see, in this model, what we have are just 3 beams and a solid body. It's meshed like this, right? Nothing special to it. What I also have is several contact options that I can go over. Now for this contact pair, it's just an automatic surface nose to surface contact. Okay, with the contact option here is automatic nose to surface. This one is also an automatic nose to surface, even though it has a straight edge and this one has a bent edge. It's the same contact behavior. The contact edge is basically these three faces, right, that I'm doing. These 2 faces that I'm looking at. Now for the third contact pair, right, so if I use a standard automatic surface contact, it's actually not going to work very well. So if I use this contact pair, for example, right, it's actually not going to work, and that's what generates this behavior right here. That's where it generates this kind of behavior right there, right? If I pause it real quick. That's where this penetration occurs, and this penetration is what you want to prevent, and that doesn't really work with the default contact. What you can instead do is to scope both body. These are body selections, by the way, right? And then you want to select that relative to a mortar contact in the mortar option. So instead of using a general contact, you use a mortar contact, and you do this by go to LS Prepost and inserting a contact property, right? It's not there because I already have it, but that's where you can include contact property, and that's where the mortar contact is generated. Now, if you look at the actual keyword, right, and this is the actual keyword that's generated, what you do, you have a mortar option included, right? You have a 9 and 10. These are parse sets, which has a set of 2, and you have soft of 2, and you have a depth of 5, and that's what allows you to generate the correct behavior for this type of contact. Remember, this is a lot more expensive relative to a center contact, so if you have a lot of these, you can slow down your model by a lot. Okay, so that's something to pay attention to, and something you can try out to see if it works or not. Now, in terms of the other model setup, I just have the beam fixed on each end of the respective beam, and then I apply a displacement down to generate the contact, the test out the contact. Then I have a default database card and default control cards. Now, notice in the default database card, I have a couple things to know about contact. Is a GL stat allow you to basically probe interface sliding energy, and that is something that's very useful to have. Right, so for example, I can go to here. I can load in the bin.now file, which allows me to go here and then look at the GL stat. The GL stat, what that will do is it will give you a global interface sliding energy, right? And if this global interface energy is negative, you're essentially having problems, right? That's usually indicating some kind of undesirable results, like penetrations. If that's very significant, that's where you want to do some troubleshooting. What we can also do is to look at the SLE out. SLE out uh, is basically this database right here, database SLE out. So I should have it back here, right there. This LEL allow you to basically monitor the energy in your friction in your contact interface. So I have 3 different contact pair here. I can look at the friction energy, which is how you are able to sort of monitor the contact energy for each contact pair, as opposed to look at the global contact energy, which is done in the GRL stat. SLEL allow you to look at the contact energy for the individual contact pairs, which is much more useful for troubleshooting in certain situations. Okay. All right, again, if you want to overcome this, use the mortar contact for solid edge, for beam edge to solid edge contact. For beam to beam or shell edge to shell edge contact, you use a general contact, which works really well. I didn't have an example for it, but that's a pretty well-known technique that one can do. Okay, and then that basically summarizes what you do in this type of problem. Again, nodal surface for general solid to beam contact. For beam to beam contact, use underscore general. For beam edge to solid edge contact, use a mortar contact. And you can pick and choose which is which. So when you have a much more complicated problem, which is a problem that look like the original request for here, right? You can see all of these beam contact. What I would try is perhaps start with a general contact that cover all of these beams. And for the group that contacts this right here, use a nodal surface. For any location where you have a potential issue with the beam edge to the edge of the beam contact, and you don't want that penetration to occur, you can just use a mortar contact for those groups, right? So it depends on the nature of the problem and where it goes. But that's the kind of thing that you can basically use a very simple example model to figure out the technique, then apply it to a much more complicated problem. Okay, I hope this helps. Thank you very much.